Hello friends, let's welcome to my lecture on Fourier integral and Fourier transforms. Let us first discuss the Fourier integral. We have seen that Fourier series are powerful tools in treating various problems involving periodic functions, but in many practical problems we do not have periodic functions, hence it is desirable to generalize the method of Fourier series to include non-periodic functions. Let us consider two simple examples of periodic functions of period t and see what happens if we let t go to infinity. So, consider this function f t x equal to 0 over the interval minus t by 2 to minus 1, 1 when minus 1 is less than x less than 1, 0 when 1 is less than x less than t by 2, and let us assume that t is greater than 2. So, we have this graph, okay. This is the graph of f t x when we take t equal to 4. We are taking this example for values of t more than 2. So, let us first consider the special case when t is equal to 4, okay. Then the graph of the function f t x, which is 0 when minus x belongs to the open interval minus t by 2 to minus 1, 1 when x belongs to the open interval minus 1 1, and 0 when x belongs to the open interval 1 t by 2 is this one, okay. This is the graph of f t x when t is equal to 4, and this graph changes to this graph when we take t equal to 8, okay. So, this is the graph for t equal to 8. Now, when t goes to infinity, okay, here when in this example when t goes to infinity, what happens? We see that f t x goes to, let us say, f x, which is 0 over the interval minus infinity to minus 1, 1 over the interval minus 1 to 1, and 0 when 1 is less than x less than infinity. We get the definition of f x. F x will be equal to limit of f t x as t goes to infinity. It is 1 when minus 1 is less than x less than 1 and 0 otherwise, okay. So, when we consider the limit of f t x as t goes to infinity, the limiting function f x assumes value 1 over the open interval minus 1 1, else where it is 0. So, this is the graph of the limiting function f x, you can see, okay. And you can also see that this function is not a periodic function, okay. So, we get a non-periodic function when we let t go to infinity. Now, let us consider another example. Suppose f t x equal to e to the power minus mod of x for the interval minus t by 2 less than x less than t by 2, okay. So, this is the interval minus t by 2 and this is the graph of f t x, this graph of f t x, okay, this one, okay, over the interval minus t by 2 and we are assuming it to be t periodic, okay. So, by using t periodicity with period t, we can extend this graph over the whole real line, and this is how the graph of f t x looks like for all real values of x. Now, let us take t goes to infinity. When t goes to infinity, f t x, let us say, goes to f x, okay, limit of f t x as t goes to infinity we are taking as f x. So, then what will happen? F x will be equal to e to the power minus mod of x over the interval minus infinity to infinity, and this is how we get the graph of f x, okay. And you can see that this function f x is not a periodic function, okay. So, we get a non-periodic function. So, these are two examples where we have tried to show that a periodic function f t x when t goes to infinity does not lead us to a periodic function. So, how we will treat non-periodic functions, that we will see through Fourier integral, okay. So, let us consider any periodic function f t x of period t which can be represented by this Fourier series f x equal to a naught by 2 plus sigma n equal to 1 to infinity a n cos omega n x plus b n sin omega n x, where omega n we are writing as 2 pi n over t, because f t x has period t, and in the case of period t we know that we get the terms in cosine and sine as cosine 2 pi n x by t sin 2 pi n x by t. So, for convenience we are writing 2 pi n by t as omega n. So, we get this Fourier series for the function f t x. Now, let us take t t goes to infinity here. Okay. So, if we take t goes to infinity and assume that the resulting non-periodic function f x is absolutely integrable. Okay. So, this condition we put on f x, okay, that f x is absolutely integrable, meaning that integral over minus infinity to infinity mod of f x dx exists, then we obtain f x equal to 1 over pi integral 0 to infinity a omega cos omega x plus b omega sin omega x d omega, okay, where a omega is given by this integral over minus infinity to infinity f v cos omega v dv, and b omega is given by integral over minus infinity to infinity f b sin omega b dv. The integral on the right hand side of 1, this integral is known as the Fourier integral. Okay. The sufficient condition for the validity of this Fourier integral is given in the following theorem. If f x is piecewise continuous in every finite interval and has a left hand and right hand derivative at every point, and f is absolutely integrable, okay, then f x can be represented by a Fourier integral. At a point of discontinuity, the value of the Fourier integral is equal to the average of left hand and right hand limits at that point. So, here when we write this Fourier integral equal to f x, we are assuming that x is a continuity point of f x. Okay. If x is the discontinuity point of f, then this f x will be replaced by the average of left hand and right hand limits of f. Now, let us look at this example. Suppose we have the function f x equal to 0 when x is less than 0, 1 when 0 is less than or equal to x less than 1, less than or equal to 1, and 0 when x is greater than 1. So, this is the graph of this function. Okay. We can let us try to find the Fourier integral representation of this. We can see that it satisfies all the conditions which are stated here in the theorem. It is piecewise continuous, okay, in every finite interval. It has left hand right hand derivative at every point, and it is absolutely integrable. We can see it is absolutely integrable. Integral over minus infinity to infinity mod of f x dx will reduce to integral over 0 to 1, because otherwise it is 0, it is everywhere else other than the interval 0 1 it is 0. So, 0 to 1 mod of f x is f x equal to 1, so mod of 1 is 1, so 1 dx which is equal to 1. Okay. So, the integral converges, okay, integral over minus infinity to infinity mod of f x dx is less than infinity. So, it is absolutely integrable, and therefore, we can find its Fourier integral representation. Okay. So, let us so in order to find the Fourier integral representation, we need to calculate a omega and b omega here. Okay. So, let us find the value of a omega. Okay. A omega will be equal to, let us go to the definition, minus infinity to infinity f b cos omega b db. Okay. So, using the definition of f x, it is 0 to 1, f b equal to 1, we get cos omega b dv. So, this is sin omega b divided by omega. Let us put the limits and we get sin omega by omega. Okay. Let us find the value of b omega. Okay. B omega is integral over minus infinity to infinity f b sin omega b db. So, this will reduce to integral over 0 to 1 f b sin omega b dv, but f b is equal to 1, okay, over the interval 0 1. So, 0 to 1 sin omega b dv, we integrate this with respect to b. So, we get minus cos omega b divided by omega 0 1. Okay. This is 1 minus cos omega divided by omega. Okay. So, we get the value of a omega and b omega. We put in the right hand side of the here in this equation, okay, and get the Fourier integral. So, we get the following. We get the value of a omega sin omega by omega, we get the value of b omega 1 minus cos omega by omega. Then the Fourier integral representation of f x is given by okay, 1 over pi 0 to infinity So, for integral representation, one over pi 0 to infinity a omega cos omega x plus b omega sin omega x d omega we have. Okay. So, this is 1 over pi 0 to infinity we get a omega equal to sin omega by omega cos omega x plus b omega is 1 minus cos omega by omega, okay, and then sin omega x d omega. Okay. We can simplify this, we can write sin omega as 2 sin omega by 2 cos omega by 2, 1 minus cos omega as 2 sin square omega by 2. We will have 1 over pi 0 to infinity, we will have 2 sin omega by 2 cos omega by 2 divided by omega cos omega x plus 2 sin square omega by 2 over omega sin omega x d omega. Okay. And this will be 2 over pi sin omega by 2 we can write outside. Okay. So, 2 over pi 0 to infinity sin omega by 2, okay, and we get then cos omega by 2 cos omega x plus sin omega 2 omega by 2 sin omega x, that is cos omega x minus half d omega. Okay. So, we get the Fourier integral representation of f, and this will be equal to f x at each point of continuity of f. Okay. This will be equal to f x when x is a continuity point of x, at each when x is a continuity point of f. Okay, when x is a continuity point of f, okay, and when you take any discontinuity point, then it will be average of left hand right hand limit. Now, we have to find the value of this integral 0 to infinity sin x by 2 over x. Okay. So, let us see, we consider x equal to half. Okay. So, let us take x equal to half, then what do we notice? X equal to half is here, okay, and at half f x is a continuous function. Okay. So, what we have at x equal to half is a continuity point and f half equal to 1. So, we get 1 equal to 2 over pi 0 to infinity, okay, and here what do we get? Sin omega by 2. Okay. X equal to half means cos 0 is 1. Okay. So, this divided by omega d omega we get. Okay. So, this implies integral 0 to infinity sin x by 2 over x dx equal to pi by 2, and we get this result. Okay. So, integral 0 to infinity sin x by 2 over x dx is equal to pi by 2. Now, if f is an even function in the interval minus infinity to infinity, then you can see b omega will be equal to 0, because f is an even function, sin omega b is an odd function of b. So, their product is an odd function, and therefore, integral over minus infinity to infinity f b sin omega b db will be 0. So, b omega is 0, okay, and therefore, f x is equal to, the Fourier integral reduces to f x equal to 1 over pi integral over 0 to infinity a omega cos omega x dx, cos omega x d omega, where a omega, now a omega will become twice integral 0 to infinity, this is a omega. So, if f is even, cos omega b is also even, then this a omega will become 2 times integral 0 to infinity f b cos omega b dv. So, f x will be given by this integral, where a omega will be given by twice integral 0 to infinity f b cos omega b dv. If f is an odd function, okay, then b omega will become double, b omega will become twice 0 to infinity f b sin omega b db, while a omega will become 0, because a omega is integral over minus infinity to infinity f b cos omega b db. So, when f is odd, cos omega is even, their product will be odd, and therefore, their integral over minus infinity to infinity will be 0. Okay. So, f x will be equal to 1 over pi integral 0 to infinity b omega sin omega x d omega, where b omega is given by this twice 0 to infinity f v sin omega b dv. Now, the integrals 2 and 3 are called Fourier cosine and sine integrals. So, this is called as Fourier cosine integral, okay. This one is called Fourier cosine integral, this one is called Fourier sine integral. Now, just as in the case of half range Fourier series, okay, a function defined over the interval, suppose a function there in the half range Fourier series, what we had a function defined over the interval 0 to L. So, over the other half interval minus infinity to 0, we were free to define in any way. So, we defined it by odd and even periodic extensions. So, when we used odd periodic extension, we found half range Fourier sine series. When we define there the function f as an even extension over the interval minus L to L, then we found Fourier cosine series. So, just like that, just like in the case of half range Fourier series, a function defined over the interval 0 infinity may be expressed as a Fourier sine or cosine integral. Over the interval minus infinity to 0, we can define by taking even extension or by odd extension. Then the function will be even or odd, and so we will get the corresponding Fourier cosine or Fourier sine integral. Okay. So, we observe that the representation of a non-periodic function f x given by 1 is similar. Now, you can see here this integral, you can see Fourier cosine integral. This Fourier cosine integral is similar to the Fourier series. Okay. So, given by 1 is similar to the representation of a function by a Fourier series, except that the range is now minus infinity to infinity and the summation has been replaced by integration. So, there also we had a similar situation. We had a n cos n x plus b n sin n x, and so it is similarly similar expression. Here there we had summation, here we have integration. Okay. And there we had the interval minus pi to pi, here we have the interval minus infinity to infinity in the Fourier integral. So, it is similar to the Fourier series. So, this is what we have observed here. Let us now move to inversion formulae for Fourier transforms. Now, the equation 1 can be written in the following manner. This equation, okay, f x equal to 1 over pi 0 to infinity a omega cos omega x b omega sin omega x. Let us put the value of a omega and sin b omega here. What we get? 1 over pi 0 to infinity a omega is integral over minus infinity to infinity f b cos omega b db, okay, into cos omega x plus integral over minus infinity to infinity f b sin omega b db into sin omega x d omega. Okay. So, I can write it as 1 over pi integral over 0 to infinity integral over minus infinity to infinity, okay, f b into cos omega t minus x b minus x db, b minus x db d omega. Okay. So, we can write like this. Now, cos omega b minus x is an even function of omega. So, we can make it 1 over 2 pi integral over minus infinity to infinity f b cos omega b minus x db d omega. This is because cos omega b minus x is an even function of omega. Okay. So, let us now go there. Okay. So, this is how we can use the fact that cos omega x minus b is an even function of omega. So, we can write fx like this. Now, sin omega x minus b is an odd function of omega. Okay. Therefore, integral over minus infinity to infinity, integral over minus infinity to infinity f b sin omega x minus b dv d omega will be equal to 0. So, I can multiply by I over 2 pi, it will be also 0. So, 0 equal to I over 2 pi integral over minus infinity to infinity, integral over minus infinity to infinity f b sin omega x minus b dv d omega. Now, let us add this quantity to this equation to this equation. Let us add 5 and 6. Okay. What we will get? We will get fx equal to 1 over 2 pi integral over minus infinity to infinity, integral over minus infinity to infinity, and here cos of theta plus I times sin of theta. So, e to the power I theta we will you write. So, e to the power I omega x minus b dv d omega. This is known as complex form of the Fourier integral. Okay. We may write this as 1 over 2 pi integral over minus infinity to infinity e to the power I omega x into e to the power minus I omega b we have here. So, I can write e to the power I omega x here, integral over minus infinity to infinity f b e to the power minus I omega b dv d omega. Okay. This I can write as 1 over root 2 pi integral over minus infinity to infinity f omega. This I write as 1 over root 2 pi we take from this coefficient and define the integral minus infinity to infinity f b e to the power minus I omega b db as root 2 pi into f omega. Okay. So, this is f omega actually. Okay. So, this is f omega and then we get 1 over root 2 pi integral over minus infinity to infinity f omega e to the power I omega d omega. Now, the function f omega given by this equation 9 is called the Fourier transform of the function f x. The function f given by this equation f x equal to this. Okay. This is known as inverse Fourier transform of f omega. Okay. Some people take 1 here. Okay, in f omega, and while taking the inversion formula they take 1 over 2 pi here. Here we have taken 1 over root 2 pi here, 1 over root 2 pi here. So, there is no problem, because when we use these Fourier transform in the solution of partial differential equations, there first we apply the Fourier transform, then we take the inverse Fourier transform. So, this coefficient is taken into account there. So, we now in a similar manner let us see how we define the Fourier sine and cosine transforms and their inversion formulae. Let us see how we find. Okay. So, from equation 2 and 3, let us look at equation 2 and 3. Okay. This is equation 2, this is equation 3. So, you put the value of a omega here, but you get 2 by pi integral over 0 to infinity a omega is f b cos omega b dB. Okay. Okay, 2 over pi integral over 0 to infinity, and let us write it as integral over 0 to infinity here of b cos omega b dB. Cos omega x d omega. Okay. So, this can be written as 2 over pi, we have two integrals 0 to infinity f b cos omega b cos omega x dB d omega. Okay. Now, let us see how we define Fourier sine and cosine transforms. So, we can write it as integral root 2 over pi 0 to infinity f c omega cos omega x d omega. Okay. So, we can write it like this. This is equal to root 2 over pi 0 to infinity, okay, root 2 over pi 0 to infinity f b cos we interchange the order of integration. So, we have instead of dB d omega, now we have d omega dB. Okay. So, cos omega b d omega we have, okay, and outside we have cos omega x d omega. Okay. So, then we define it right like this, 2 root 2 over pi 0 to infinity f c omega cos omega x d omega, where f c omega is equal to root 2 over pi 0 to infinity f b cos omega b dV. Okay. So, this is defined as Fourier cosine transform of f, and this formula which gives the f x. Okay. This formula f x equal to this. Okay. F x equal to root 2 over pi 0 to infinity f c omega cos omega x d omega is called the inversion formula for the Fourier cosine transform. Similarly, we have the formula for Fourier sine transform. You put the value of b omega here, 2 times 0 to infinity f b sin omega b dV, interchange the order of integration. So, after interchanging the order of integration, root 2 over pi integral over 0 to infinity f b sin omega b dB, sin omega b d omega, okay, sin omega b dB. Okay. F s omega will be equal to root 2 over pi 0 to infinity f b sin omega b dV. This will be Fourier sine transform, and inversion formula will be f x equal to root 2 over pi 0 to infinity f s omega sin omega x d omega. Okay. Simple, in a similar manner we do it. Okay. Just like in the case of Fourier cosine transform, we put the value of b omega from here in this integral, and we get the Fourier sine transform and Fourier inversion formula for Fourier sine transform. Okay. So, this is formula for inversion formula for Fourier cosine transform, this is formula for Fourier cosine transform, this is inversion formula for Fourier sine transform, this is Fourier formula for Fourier sine transform. Okay. So, the equations now let us look at this. The equations 10 and 12 give the inversion formulae for the Fourier cosine and sine transforms. This one and this one, they give the formulae for the inversion formulae for the Fourier cosine and sine transforms of f, okay, which are given by 11 and 13. Now, note that some authors take the coefficients in the Fourier sine and cosine transforms as 1, and in their inversion formulae 2 over pi instead of root 2 over pi each taken by s. This does not make any difference in applications to the solutions of physical problems. Okay. Now, let us take this example. Suppose we have an integral equation, because we have here unknown function f x, it occurs inside the integral sign. So, integral equations can also be solved using the Fourier cosine sine transforms. So, 0 to infinity f x sin a x dx is given equal to 1 when 0 less than a less than 1 and 0 when a is greater than 1. We have to find this unknown function f x. Okay. So, let us compare this with the Fourier sine transform. Okay. So, this is the Fourier sine transform, okay, 0 to infinity f b sin omega b dB into root 2 over pi f s omega. Okay. So, we are given f s omega. Okay. So, here we are given Fourier sine, instead of omega we have here a. Okay. We do not have sin omega x, we have sin a x. So, we have f s a, and root 2 over pi I am taking as 1 instead of root 2 over pi here for convenience. I am taking it as this coefficient as 1. So, while taking the inverse Fourier sine transform, I will take here 2 over pi. So, f s a is given to be 0 to infinity f x sin a x dx equal to 1 when 0 less than a less than 1 and 0 when a is greater than 1. Okay. Now, then by inversion formula f x will be 2 over pi 0 to infinity f s omega sin omega x dx d omega. Okay. Why I have to use sine inverse for Fourier sine transform? Because we have sine function here. If we have cos ax function ax, then we will use Fourier cosine transform formula. So this is equal to 2 over pi, and over the interval 0 1 it is 1, otherwise 0. So 0 to 1, fs omega is 1 sine omega x d omega. So this is 2 over pi minus cos omega x over x, because we are integrating with respect to omega 0 to 1. Okay. So this is 2 over pi 1 minus cos 0. Okay. So this is 1. No, we have 0 1 interval. Okay. So when 0 it is will be 1. Okay. 1 minus cos x by x, because these are the limits for omega. So 1 minus cos x by x. So we have 2 over pi into 1 minus cos over x, cos x over x. Now application to partial differential equations. Integral transforms can be used to find the solution of partial differential equations. The choice of a particular transform to be used for the solution of differential equation depends upon the nature of the boundary conditions of the equation and the facility with which the transform f omega can be inverted to give fx. Let uxt and ux, okay, be functions which tend to 0 as x goes to plus minus infinity. Then the Fourier transform of uxx is given by f uxx equal to minus omega I square uxt. We can see this Fourier transform of uxx. Okay. Let us go to the formula for Fourier transform. So Fourier transform is 1 over root 2 pi. I will take here 1, and then while we take the inversion formula, we will take 1 over 2 pi here. So f omega is minus infinity to infinity f b e to the power minus I omega b dv. Okay. Let us use this formula. So this will be integral minus infinity to infinity uxx e to the power minus I omega x dx. Okay. This will be now let us integrate it by parts. So we will have ux, when we integrated with respect to x, ux e to the power minus I omega x minus infinity to infinity minus infinity to infinity ux minus I omega e to the power minus I omega x. Okay. Now ux goes to 0, we have assumed ux goes to 0 as x goes to plus minus infinity. So this will go to 0 when x goes to plus infinity, and this will also go to 0 when x goes to minus infinity. E to the power minus I omega x is a bounded quantity, because mod of e to the power minus I omega x is equal to 1. Mod of e to the power minus I omega x is under root cos square omega x plus sine square omega x. So that is 1. So bounded quantity multiplied by 0. So we get 0 here, and this becomes I omega integral over minus infinity to infinity ux e to the power minus I omega x dx. Okay. And we integrate it again. So when you integrate it again, what you get? I omega integral of ux is now x. So uxt into e to the power minus I omega x minus integral over minus infinity to infinity uxt into minus I omega e to the power minus I omega x dx. Okay. So this will again go to 0, because we have assumed that uxt goes to 0 as x goes to plus minus infinity, and e to the power minus I omega x is a bounded quantity, it is bounded by 1. So this will go to 0, this will go to 0. Okay. And we will have then I omega into I omega. So I square omega square, I square is minus 1. So we will get minus omega square, and we will get integral over minus infinity to infinity uxt e to the power minus I omega x dx, which is Fourier transform of uxt, and we are denoting it by uxt. Fourier transform of uxt we are denoting by, you can see here, Fourier transform of uxt we are denoting by uxt. So Fourier transform of uxx is minus omega square uxt. Okay. If us omega t and uc omega t are Fourier sine and cosine transform of uxt, then us omega t is equal to integral 0 to infinity uxt sine omega x. This is how we denote the Fourier, this by this notation we are denoting the Fourier sine transform of uxt. Okay. So, Fourier sine transform of uxx then will be given by this formula, we can easily see that. So, Fourier sine transform of uxx will be then uxx will be integral 0 to infinity uxx sine omega x dx. So, integrate by parts. So, ux sine omega x 0 to infinity minus ux, we are integrating with respect to x. So, omega times cos omega x dx 0 to infinity. Now, ux goes to 0 when x goes to infinity, and sine omega x is a bounded quantity, is bounded by 1. So, it is 0, and when x is 0, sine omega x is 0. So, this quantity becomes 0, and what we get minus omega integral 0 to infinity ux cos omega x dx. Let us integrate by parts again. So, we get uxt function now, integral of ux is uxt cos omega x 0 to infinity minus 0 to infinity uxt into minus omega sin omega x dx. Okay. When x goes to infinity, we have assumed u goes to 0. So, this goes to 0. When x goes to 0, this becomes u minus u0 t cos 0 becomes 1. Okay. And here we get plus omega Fourier sine transform of uxt. Okay. So, because we are getting this omega times 0 to infinity uxt sine omega x dx. Okay. So, what we get, let us see, we get minus omega we got outside, and then we get here minus omega square. Okay. So, minus omega square fs u xt be denoted by us omega t. Okay. Us omega t, and this will be omega uxt at x equal to 0. Okay. So, omega uxt at x equal to 0 minus omega square fs uxt, which is us omega t. In a similar manner, we can derive for the Fourier cosine transform the formula fc uxx equal to minus ux at x equal to 0 minus omega square uc omega t. Now, when we apply these sine transform or cosine transform to the partial differential equation, we have to see the boundary condition. If the boundary condition is given at x equal to 0, we are given u0 t, then we apply Fourier sine transform. If we are given the gradient at x equal to 0, that is ux at x equal to 0, we apply Fourier cosine transform. So, we can decide from the boundary conditions which transform we have to apply in case of a semi infinite domain. Okay. Here we are using integral over minus integral over 0 to infinity. If we use integral over minus infinity to infinity, if we are given the problem over minus infinity less than x less than infinity, then we will need to use Fourier transform. So, let us apply this Fourier transforms to solve partial differential equation. In one dimensional problem, the PD is transformed into an ODE by applying a suitable transform. If in a problem uxt at x equal to 0 is given, then we use Fourier sine transform to remove uxx. In case ux at x equal to 0 is given, then the Fourier cosine transform is applied to remove uxx. Let us determine the distribution of temperature in the semi infinite medium x greater than or equal to 0 when the end x equal to 0 is maintained at 0 temperature. So, we are given u0 t, x equal to 0, t is given as 0, okay, u0 t is given as 0, and initial distribution of temperature is e to the power minus x. So, we have ux0 equal to fx equal to e to the power minus x. Okay. Now we know that the heat equation in one dimensional heat equation is given by one dimensional heat equation is given by ut equal to c square uxx. Now we are given uxt at x equal to 0, so we will use Fourier sine transform. So we will apply Fourier sine transform here. Okay, so we multiply this equation by Fourier sine transform we have to apply. Okay, so we will multiply this equation by sine omega x and integrate with respect to x. Okay, so let us multiply by sine omega x. And integrate with respect to x over the interval 0 to infinity. Okay. So then x and t are independent of each other. I can write it as d over dt of derivative with respect to t of integral 0 to infinity uxt sin omega x dx, and this is c square times Fourier sine transform of uxx. So we have seen Fourier sine transform of uxx is given by omega times uxt at x equal to 0 minus omega square us omega t. uxt is equal to 0 when x equal to 0. So it reduces to minus omega square us omega t. So we get minus omega square us omega t. Okay. So left hand side is this is us omega t. Okay. So we get d over dt us omega t equal to minus c square omega square us omega t. Okay. So this is dy over dt equal to minus c square by square c square w square by. So we can integrate it easily now. Okay. So we get us omega t equal to some constant a times e to the power minus c square omega square t when we integrate with respect to t, keeping omega as constant. So this a will depend on omega, a will be a function of omega. Now let us take let us use this boundary condition. Okay. So we are given that integral 0 to infinity uxt sin omega x dx, this is equal to us omega t. This is what we have assumed. So put t equal to 0 in this. So us omega 0 will be equal to integral 0 to infinity e to the power minus x, because uxt is ux 0 which is e to the power minus x sin omega x dx, and its value is omega over 1 plus omega square. Okay. So put t equal to 0 here. So us omega 0 becomes omega over 1 plus omega square, and this is a omega and this is 1. Okay. So we got the value of a omega. Okay. So thus we get us omega t equal to omega over 1 plus omega square e raised to the power minus c square omega square t. Now we take the inversion formula, use the inversion formula. So we take the inverse Fourier sine transform of this. So taking inverse Fourier sine transform we get uxt equal to, we multiply by sin omega x and integrate with respect to omega. Okay. Now we have taken, while taking Fourier sine transform, we have taken the coefficient as 1. So here we will take the coefficient 2 over pi. So 0 to infinity omega over 1 plus omega square e to the power minus c square omega square t into sin omega x d omega. Okay. So this is the temperature distribution in the semi-infinite medium for x greater than 0, t greater than 0. Okay. So, this is what we have 2 over omega 0 to infinity omega over 1 plus omega square e to power minus c square omega square t sin omega x d omega. With this I have come to the end of this lecture. Thank you very much for your attention.